Saxon Algebra 2, Lesson 51. Greetings, my students. Just a reminder that whatever I write down here, I want you to make sure you write down too. Please pause me. I'm trying to do better about taking time, but I'm being really bad. Because you know why? I love these lessons and I'm too excited and I'm going fast. But trying to remind me, this is another lesson, you guys, that is just a gem and a half. So stick with me. We're going to start by talking about pig houses. This is technically example 51.1, but I think John misnamed it. I don't think this should be an example. Anyway, there's three parts to it. He wants to remind us that if we have two pigs in separate houses, we can combine them. Whoops. And just multiply them together and put them together in the same pig house, right? That's cool. Now, we can also do this if we can do this very easily. If they're both negatives, that becomes very easy. We put them in together, -3 times -2. And we follow our same rule that 2 pigs in the house equals 1 pig out of the house. But we can do it with the signs as well. So the 2 signs can jump out. And so our final answer for this would be -√6, right? Because the 3 and the 2 have to stay in because they're separate pigs. But the 2 minus signs can jump out. 2 in the house equals 1 out of the house. So there it is, all right? Either of these two situations are perfectly fine. They are, in fact, what I would describe as A-OK. Okay? A and B are A-OK. Here comes a third scenario that is drama, drama, drama. The third scenario is when one of the pig houses is positive and one is negative. Because when you put them together, there's only one negative sign, so it cannot jump out, and instead we're left with this. Now, this is the correct answer, but this number makes no sense because what we're saying is it's a square root, right? There's no 2 written there, but we could put it there. What are 2 numbers that multiply together to equal -6? Now, we can handle the 6 part, but there's no 2 numbers that multiply together to give you a negative. It's impossible. There's no way that could ever happen. There's no number possible to do that. So we say that this, let me just write this here for purposes you'll understand in a second. This is called an imaginary number. We cannot have a negative root, a negative even numbered root. It's okay for odd numbers, but for even numbers, we can't have an even numbered root. And if we say that we do, we have to call that an imaginary number, and we have to have a different way of signifying that, okay? So again, this comes up when we have one minus sign inside of a pig house, all right? 2 minus signs in a pig house are fine. They jump out just like pigs. But, and this is what I meant when I say they're A-OK, that means these 2 scenarios are both real numbers. This is not a real number. This is an imaginary number. It doesn't exist on a number line, and we have to figure out what to do with it. Now, lucky for us, there was, in the 1700s, in Switzerland, there was a mathematician whose name was Euler. He spelled it like this, but it was pronounced like that, Euler. He was in the 1700s. He was Swiss. He was a cool guy. He made several nifty contributions. He made 4. I'm going to write them up because I'm such a fan of his. He's the one who came up with this sigma that means summary that you'll learn to do. Let's see, the older girls learned how to do this quite recently. He invented functional notation, so the whole f of x drama, that was Euler. He made that up. And when we learn about logarithms, which I'm not sure if we've done yet, there's something called the natural logs. which are a basis of e. He came up with that. But our thing that he came up with is he came up with the notation of I for imaginary numbers. Yes, I want you to write all this down because he was such a cool dude. So here's what he said. When we get something like this, whoa, -6, sorry, I forgot that. We're going to recognize that we can break that into two parts. We can put the minus sign on a 1 and then multiply it by the 6. Then what we're going to do is going to make a rule that anytime we have a negative square root of 1, we're going to call that I. That's a lowercase letter I with a little bit of a curly tail, so it looks different. And then we'll be able to write this as square root of 6 I, right? Because we turn this -1, it's the square root of -1, we turn that into the letter I. And then whenever we have 2 i's, that just becomes -1. Okay, which makes sense because if one of them is the square root of -1, then when you square them, blah, blah, blah. Okay, so those two go together. They're not two different things. That's just two ways of saying it. So our friend Euler has given us a tool to use when we create these imaginary numbers by having minus signs in the pig house, and we can use it. So let's just do some great examples. -13 minus 13 square root equals square root of 13, and the -1 that was attached to comes out as an I. -4, whoops, I'm sorry, I forgot the minus sign in there. Okay, in this case, the square root of 4 part, we can change it and write it like this, right, if that helps us. And then that becomes 2I, right? So we can simplify the radical part. And then the last one, C, is square root of 3 times the square root of -2. Okay, we talked about that. That creates a problem for us. So that would be square root of -6, and that would be square root of 6I. So these are just some little practice problems to help us figure out how that notation works. We're going to do more as we go. Okay, now that's imaginary numbers. Okay, so he said imaginary numbers are a thing. They don't exist on the number line. They're just weird little freaks, but we can recognize them and play with them. Now he said, okay, let's come up with a duo. Let's call them complex numbers, and we'll say that they take this form. We'll say a complex number has a real number and an imaginary number. So we can see all numbers as fitting this format, all right? If it's just a plain real number, we would say it's this part with 0I, right? And I'll show you an example in a minute. We just have one more type of problem to figure out. A complex number is a number that has a real part and an imaginary part, and any number can be expressed as a complex number. We'll get to that. How do we work with them? They're pretty easy and kind of fun. We're going to add 4 plus 6I plus 3I minus 2. We just add the real parts and the real parts and the imaginary parts and the imaginary parts. So real and real equals 2, right? 4 minus 2 is 2. And imaginary and imaginary, 2 plus 9I. That's easy, right? Let's do another one. Add. Okay, this one looks crazier. We're just going to have to sort through it a little bit. I'm copying. You copy too. Okay, this is as much order of operations nonsense as it is anything else. Remember that when we put parentheses around binomials, if it's positive in front of them, we can just take the parentheses off and leave the signs as they are. If there's a negative, we have to distribute it to what's inside the parentheses that come after it. So we can get rid of these parentheses, but we have to clean this up as we go. This one's fine, it's an implied there. So 4 minus 3i plus 6 minus 4i, whoops, I'm going off the line. Now these change, minus 2 plus 10i. See how this minus sign flipped those. Okay, notice that in these, some of them are in the proper format with the real number and then the imaginary. Real number, oh no, they all are, sorry. Sometimes in problems they'll get flipped around. That's okay. We can change the order as we work, but when we're done, we always want to have this order for our answer, okay? So now the same thing happens now that we remembered our order of operations rules about parentheses and symbols of inclusion. Now we can just go through. Here's a 4, a plus 6, and a minus 2. 10 minus 2 is 8. And then we'll just combine these. That's minus 7 plus 10 will be plus 3i. Oh, I see what I did wrong. I multiplied that by 2. I just got crazy there. This should be 5i. So this answer changes to 8 minus 2i. My bad. Did you see what I did? I just got so excited with distributing this minus that I decided to multiply it by 2 as well. Just feeling creative today, you guys. Sorry about that. Okay, that's the right answer. So sorry. All right. Now we're going to do 2 more problems and then we'll be done with this lesson. And they're a little bit different and a wee bit trickier, but honestly, these aren't even fun. They're so easy. Ready? Remember that I told you that every 2 i's equals a minus 1? We're going to use this rule now. Okay, I'm going to copy. It's a lot. Okay. This should be a minus. Okay. So here's what we're going to do. We're going to take a look at this because if a number has more than 1 I after it, we might be able to use this rule. So right here, for example, we see there are 2 i's. Well, that simplifies to minus 1. So we can change that into a minus 2, right? It changes the sign. This was plus before. Same thing here. There are 3 of them. So we can take 2 of them, turn them into a minus 1, change this to a plus, and then we'll have 3, and then we'll have 1 I left over. Okay? This one is going to stay the same. Minus 4, that stays the same. Now let's look at all of this. This is a minus sign. This needs to be fixed because it's an imaginary number we can see. So we need to change it into square root of 4 times square root of minus 1. Square root of 4 is 2i. Okay, so this minus sign we took care of, but this one exists. And that is the simplified version of this last term. Okay, now we're ready to do what we were doing before. First, we'll gather up all of the real numbers, and we get minus 6, and then 3i plus 2i minus 2i. Okay, so that's plus 3i. Final answer. Yay! Okay, and there's one more. 51.6. Ready? This time, instead of writing the i's out individually, we're going to use exponents. So 3i cubed plus 2i squared plus 7i plus 4 plus 2i to the 5th. Okay, if you would like, you can write these out, right? 3i plus 2i. A lot of students will choose to write these out because it's easier to circle the pairs and change the signs. When you're feeling comfortable, you can just do it as a mental process, working from here. I'm going to show you how to do it this way again so that it's crystal clear, and then you can decide for yourself whether you're ready to jump into the mental process or whether you want to write it out, right? So I just made the same number of i's as the exponent said. Those two make a -1, so this becomes minus 3i. These two make a minus sign, so it's -2. There's nothing left. This stays the same. This stays the same. Now look at this one. This one's crazy. That makes a -1. That makes another -1. So I'm multiplying this by +1, so it stays the same, like so. All right, real number, we get 2. And then imaginary, we get 9, so it's +6, yes. Okay, so writing out the i's helps you pencil and paper your way through this. If you feel comfortable doing it in your head, go for it. If you get it wrong, slow down and try this again. All right, you guys, we have now moved beyond the realm of real numbers. We are in Mordor, which sometimes is what imaginary numbers feel like. But that's a huge step in your math education. I'm very excited to introduce complex numbers to you today. That's the end of lesson 51. 52 is another gem, you guys. We are killing it this week. And I look forward to seeing you in lesson 52.